Thank you very much. I'm going to give an argument about why we might want to learn more about this, and I'll say a little bit more about some recent research I've done that may give you a sense of what's possible and also how much easier it is to come up with new ideas that might be interesting compared to the difficulty of actually figuring out their environmental risks or effectiveness. And in that sense, I think what I'm saying is quite in line with what you just heard. So there's no question that large-scale climate engineering is untested and dangerous. I think I would disagree quite strongly that it is doesn't exist. I think that the capacity to do it in engineering terms most certainly exists, and that's part of the reason we have to think seriously about how we manage that and how we build tools for figuring out how we regulate and manage that capacity, which I think is, in the sense that we have the capacity to build tall buildings or something, it's more or less a fact that if we wanted to, we could do this. And that itself has profound policy consequences. And I'm going to illustrate a little bit why I think that that's a reasonable statement. Let me first give you something that you could call a pitch, which is why it makes sense to think about understanding the effectiveness of this and perhaps building the capacity to do it contingent on what happens to the climate. So as presumably you all know, the amount of climate change we get for a given amount of CO2 emissions is still deeply uncertain by factors of 2 or 3, and the effects of climate change on, say, the cryosphere, the big ice sheets, are even more uncertain. So the climate problem has uncertainty at its heart. We don't know what the consequences of putting all that CO2 in the atmosphere will be, and this is crucial, CO2 lasts for a very long time when we put it in the atmosphere. The CO2 we put in the atmosphere, unless we have a technology for pulling it out later, the CO2 we put in the atmosphere has a footprint that lasts for thousands of years. A footprint, you might argue by some measures, that lasts much longer than the footprint of nuclear waste. And it's the combination of those two things, the uncertainty about the problem and the length of time of the footprint, that makes this problem so hard to manage. If you had only one of those things, it's much easier. Let's think a little bit more about inertia in the policy side as well. So we ought to have started, arguably, in 1965, when the first high-level report got to President Johnson explaining the dangers of putting all the CO2 in the air. We ought to have started to think about reducing our emissions, but clearly we didn't. When we actually have serious climate policy, which should have been decades ago but isn't yet, that policy is effectively going to build low-emission infrastructure, replace the high-emission infrastructure we have now. But that's a very slow process because you've got to build all the capital stock of infrastructure, all the solar panels or windmills or nuclear power plants or whatever is your preference. And that capital stock builds slowly, and the emissions reductions are proportional to the amount of that low emissions stock you have. But emissions reductions don't directly affect the climate. It's the concentration, the buildup of CO2 in the atmosphere that affects the climate, and that's a second integral. And this makes this thing have enormous inertia. So from the time that we decide seriously to begin to pull emissions down, to the time that we see a big effect on the climate, has a timescale of order a century, or a good fraction of a century. And so it's that combination of uncertainty about how bad the climate response is and inertia that is, at least for me, one of the principal reasons that we might want to know something about these technologies. That's something both about how they work technically and beginning to think about how we'd actually manage them in terms of governance. Just to be even one more step precise, the point is, at some point, which could already be today, or could be 10, 20, 30, 40 years in the future, we may have put enough CO2 in the atmosphere that we'll have unacceptably huge responses to that CO2. And at that point, stopping emissions doesn't solve the problem. So it's common to frame this simply as a trade-off between doing geoengineering and cutting emissions. And there's no question that if you think about this as an optimization problem, there's some trade-off. But it is not simply a trade-off, because cutting emissions can reduce the amount of CO2 we're going to put in the atmosphere in the future, but it does nothing to manage the amount of CO2 we have already put in the atmosphere. And the various kinds of geoengineering could potentially do that. So let's start out by distinguishing two totally different sorts of things that have both come under the name geoengineering, but I think have very little to do with each other with respect to the underlying science technology, with respect to the costs, and with respect to the social science and governance issues they raise. So one of those things is the thing that I'll mostly talk about, and I'll give you some specific new research on, is how we might manage or control or affect, is maybe a more honest word, the amount of sunlight that the Earth absorbs. And I'll come back to that in a minute, but the key factors are this is fast, it's cheap, and it's inherently imperfect. It cannot compensate for the amount of CO2 in the air. There are a bunch of other things we might do to remove CO2 from the air. There's a big list, and full disclosure, one of those on the list, the direct capture of CO2 from the air, I work on a commercial basis. I do absolutely no proprietary commercial work on soil radiation management because I think such work would be wrong. But on carbon cycle engineering, there's a whole range of things we can do, but all of those things are inherently slow and expensive. But on the upside, they actually get the CO2 out of the air, which is the root problem, and in some sense would allow you to go backwards. So partly because it's fun new work, and that's the point of conferences, and also because it raises a bunch of the key governance issues in interesting ways, I'll tell you a little bit about some new work we've been doing, thinking about how you actually might put aerosols in the stratosphere. And lists some of my collaborators. So almost all the work, not all, but almost all the work and almost all the modeling that's looked at putting sulfate aerosols in the stratosphere has assumed that we'd mimic volcanoes. And there's a lot of sense to thinking that we mimic volcanoes because we have some sense of what's happened after volcanoes. The planet cooled, there were impacts on ozone, there were impacts on the biosphere, we were able to monitor them. But there's some reason to think that for continuous injection this won't work very well. And the reason basically is the way those things work is you put a gas which does not condense, SO2, into the stratosphere. And the only way it makes particles is it converts to H2SO4, sulfuric acid, and then that stuff, which isn't volatile, condenses onto particles. And that automatically happens slowly if you're putting a gas in like SO2. And because it happens slowly, you necessarily find that almost all of the new mass you put in ends up on existing particles, either directly or by making ultrafine particles that then coagulate with the big particles. And so the problem is you end up making particles that are too small, too large, if you do this continuously. This gives you a sense of how important particle size is. So on the x-axis, sorry, you can't read as well as radius in microns. And look at the alumina or sulfuric acid functions, which are the mass-specific backscatter. So a measure of radiative forcing, and in fact I have it in watts per square meter per megaton. And those things fall off as the particles get larger. But even more important, the fall speed rises quite rapidly in this regime. And so as particles stick together and get large, they fall out of the stratosphere very quickly. And so particles that are too large are much less effective per unit mass. So a bunch of colleagues, of whom I wasn't one, published an article that was the first article to really, or first study to attempt to do full microphysical studies of particle formation in the stratosphere. The previous modeling experiments have either just prescribed a change in solar forcing, or they put in sulfur, but they haven't allowed the sulfur to determine what size the particles were. That's not quite true, but it's almost true. And what this result found, which used a sort of state-of-the-art 2D model that's been tuned up on the Pinatubo experiments, is if you put sulfur in continuously, you get, at least in this version of the model, but we think the underlying physics is pretty robust, although the numbers aren't, you actually get a remarkably ineffective result. So you have to put a great deal of sulfur in to get enough radiative forcing. If you look on that right-hand one, even if you put 10 megatons a year of sulfur in, which is a huge number, by this model you only get about a watt 0.7 of radiative forcing, which is much, much smaller than previous predictions. And that's because you've grown particles that are too large that are falling out very quickly. And there may be some ways around that, but that underlying fact that if you put in a gas, the gas all ends up in the existing particles, the particles get too big and fall out, is pretty likely a robust result. So more or less you could say this says that the standard way people have thought about doing this doesn't work, or at least doesn't work very well. The novel method we've been thinking about, or it's not novel at all, it's actually exactly what happens from aircraft contrails. The novel method is that we put a condensable vapor directly out of the back of an aircraft. And that's what happens when we put water vapor out of the back of an aircraft. The water vapor cools by mixing with the ambient air, and then it condenses to form particles. That's the mechanism of contrail formation. So if you did that with H2SO4 directly, putting it in as H2SO4 instead of as SO2, you find that the formation of particles is completely dominated by dynamics that happen in the plume in a day, and essentially has nothing to do with the background particles. And we've tried this with the state-of-the-art. I mean, it's both true when you do back-of-the-envelope calculations, but also we've tried it with a state-of-the-art nucleation code, and it appears to be true in that code. This gives you a quick look. Actually, maybe I'll skip in a second. This gives you a quick look at results. If you look at the upper panel and you look at the black line, that's the particle number density. That's what happens with SO2, where you get a bunch of these very fine particles, but overall you get particles that are quite a lot larger than this. The black line on that log scale goes quite a bit more to the right. Whereas when we put particles in directly, effectively by taking the output of the plume model and feeding it into the 2D model that does particle size dynamics, we get results that are much more effective. I'll skip this. And that's one of the preliminary answers. We're actually looking at two different radiation codes, so this is not exactly the same as what I showed you before, but the ratios are the same. When we put in particles directly, we get a much more effective system. So we can find that a few megatons a year of sulfur would be enough to produce sort of 4 watts per square meter radiative forcing. Not that there's any reason you should want to do 4. I think some of the conversation about geoengineering has been caught by a kind of foolish dichotomy between doing nothing or doing enough to compensate for 2 times CO2. I think it's almost certain that would not be sensible policy. But nevertheless, at the level of simple modeling, this gets you a sense of how much more effective it is if you can control the particle sizes better. So thinking a little more generally, you can think that there's actually quite a few means of putting particles in the upper atmosphere, and essentially all the effort so far is focused on number 1. You put in this high vapor pressure gas, it converts to a low vapor pressure gas, and I think that inherently makes it extremely hard to control particle sizes, and I think that will be a general fact of any analog to that. We've talked about method 2, which is a low vapor pressure gas. The advantage of that is it turns out there's a huge literature in the nanofabrication world about making fine particles. I'll show you a picture in a moment from low vapor pressure gases. People understand how to do it pretty well, and there's nothing very hard in terms of aircraft engineering. If you go to aircraft engineers, and we've done this, they say, that would be easy, we could do this if you want us to. Whereas number 3 or number 4, putting in solid particles or making fine droplets, is much harder because it relies on spray technologies that may not exist yet. We've mostly thought about sulfur, and there's a lot of good reasons to think about sulfur because sulfur is what nature does, and there are very good reasons to think we would like to start very slowly if we ever wanted to do this and do something that was an analog to nature because we have some idea what the downsides of what nature does are. Nevertheless, there might be some good reasons to think about alumina. It turns out, first of all, there's been a lot of work on the environmental consequences of alumina in the stratosphere because it's in shuttle exhausts. There's a bunch of papers going back to the 70s that look at the radiative and ozone-destroying properties of alumina in the stratosphere, and those make you think it might be useful. The big deal really is that alumina has 4 times the volumetric radiative forcing for small particles as does sulfur, and that means you have 4 times less surface area for the same radiative forcing, and this is a much bigger deal. You have roughly 16 times less the coagulation rate, and that's the thing that really drives removal. So you could get away, we think, with much smaller mass fluxes, but we haven't run those studies yet, so that might be wrong. The little picture is from a nanofabrication study, which shows you can make very high quality, and do this in just a jet in a very simple way, make high quality alumina particles just by spraying aluminum vapor out, which oxidizes. So it's certainly in principle possible to do that. There's a big literature that's already looked at that. We've been doing a little work on delivery. There's a study that an aircraft engineering firm called Aurora Flight Sciences is doing, and all the results of that study will be completely public. There's nothing proprietary about this. We're going to be inviting people in for a mid-study meeting soon. And they've been looking at a bunch of different delivery options, but the bottom line is that it seems pretty cost-effective and easy to do this with aircraft that are not very different from conventional aircraft. So there's no, from their point of view, nothing radical and hard. For them, radical and hard is making aircraft that fly at 100,000 feet, but not ones that fly at 70. Give you a little sense of some of that. One thing that study's turned up is that some high-class business jets, like the Gulfstream, have wing designs that are very efficient. So with slightly different engine choices, they can easily deliver large weights up to sort of 20 kilometers or a little higher. And you could do that by either building new versions of these aircraft or even re-engineering existing aircraft. So there's some ideas of that. There are now studies you see on the lower right. These are preliminary. Look at the total cost to deliver a megaton a year to the stratosphere as a function of height and so on. The bottom line of this is simply sort of confirming earlier work that Alan's done, that it's so cheap that it doesn't matter. So the fact that it's cheap isn't necessarily a good thing at all, as I'll come to in a second. The fact that it's cheap is part of the hard problem of governance. The fact that it's cheap means any small state or even conceivably individuals could do this, and that is a very dangerous thing. So the fact it's cheap is not necessarily good, but I think it more or less is a fact. So this is where I would push back on the statements that it doesn't exist. I mean, it doesn't exist in the sense that you can't just do it today, but exists in the same sense that if you wanted to build a kilometer-high building or lots of big ships today, we have engineering firms that can do it. So you go to an engineering firm and you want this done. They don't say this is hard or unusual. They say, okay, yes, we could do it. So a few closing thoughts on this. What I said at the beginning, it's much easier to think of new methods that might conceivably offer lower environmental risk for the same rate you do forcing than the existing methods. That's the point of this from my point of view. There's a huge scope for new methods, because once you realize you can make things by direct condensation from vapor, then all sorts of different compounds are possible. But it's much, much harder to actually figure out the environmental risks and effectiveness of these new methods than it is to cook them up. And that is going to be a fundamental ongoing problem here. So now coming back to the things I said at the beginning, I said that solar radiation management was cheap, fast, and imperfect. Now let's think about the policy consequences of being cheap, fast, and imperfect. So, oh, sorry, I've repeated the slide. The policy consequence of it being cheap is control. So if you think about the problem that we have for controlling CO2 emissions in the atmosphere, the problem is to, if we want to cut emissions, get many different states around the world, many different individuals to collaborate on a very costly activity, which, I mean, I spend a lot of my life trying to convince people to collaborate on, and whose benefits are spread globally. And that's inherently a hard thing to do. It's the commons problem. Aerosol geoengineering looks like it is so cheap that the cost is basically not going to be an issue. That means that implementation decisions will be risk-to-risk decisions. The risk of doing it against the risk of not doing it. And it makes the problem of how we govern it fundamentally harder and different and novel. It's fast, I said that already, and it's imperfect. It's just basic physics. All the models say so, but don't believe it just because the models say so. Really, basic physics says that reducing the amount of sunlight is just not the same as reducing the amount of CO2 for a bunch of reasons. So we should expect that for fundamental reasons, you cannot compensate for the amount of CO2 in the air by doing this completely. You may or may not, in a useful way, reduce the risks, but you can't compensate in a way. And the policy consequence of that is, it is not a reasonable strategy to say that you're going to just do solar radiation management and never cut emissions. If you follow that strategy, you will end up with climate risks that are as big as the risks we have from just emitting the CO2 directly. Skip this. I want to give a very simple argument. There's various economic arguments we have for why it might make sense to do some research. And you can think about this in this simple kind of dichotomy matrix, although, of course, as I said, it's not a dichotomy. It's not like we do research or don't, or it works or it doesn't work. But on the left, we have what we expect. So we have some preconception that it will at some level work. Work, of course, doesn't mean work perfectly. Work means provide some useful reduction in the risks posed by CO2 in the air. And then we'll find out what actually happens. So the worst case for sure, and the case that I think you're tempted to think about from the talk you heard before mine, is that we expect it works and we find it doesn't. That's the very worst case, because it's going to tempt us to spend perhaps less money and less effort than we should cutting emissions. But it's important to say that there are other quadrants to pay attention to. So let's say that it works. Again, works means just provides a useful reduction in risk, and we are convinced that it doesn't work. Then we've missed a real opportunity to limit environmental damages, say damages to the high Arctic, which is not a trivial thing. So, last slide. You can present this argument, say, based on this or more complicated versions of this, that says it's really worth knowing more. More knowledge is good because more knowledge will tell us about the risks of this in a useful way. And I guess I want to add one more thing before the last slide. Another reason why I think more knowledge is good is I think this will turn out to be more complicated and harder to do than we now think. So I've told you that it's cheap to deliver materials to the stratosphere, and I'm convinced that's true. I don't think that will change. But I think the more we do research, the less easy this will look, the more complicated the environmental effects will look. And that's a good thing, because right now it looks too easy. So I think that if we do more research, we're likely to find out that it's harder and more complicated than we thought, and that the side effects are harder to manage. And that's a healthy outcome that will make it easier to do the management. But nevertheless, the underlying concern, and the reason that this hasn't been talked about until the last few years, is this so-called moral hazard. That knowledge that geoengineering is possible makes climate impacts look less fearsome, and that makes a weaker commitment to cutting now. That's the central reason that I and many of my colleagues have had real doubts about speaking about this publicly, because people, as you've heard, knew that this could be done back to the 60s in some format. Of course, the opposite reaction is possible. It's an empirical question, how people will actually react to knowledge about this. Another reaction is to say, if these crazy scientists are so concerned about putting CO2 in the atmosphere, they want to think about these things, then that might actually mean we should be more serious about the risks of CO2 in the atmosphere. And by the way, it's not really a moral hazard. It's more like free riding on our grandkids. Thank you very much.
The next speaker is Ken Caldeira. Hi, so today I'm going to talk about can intentional intervention in the climate system reduce risk? And I think the answer is we don't know, but that we should do the research to find out. Just in case there's any question about my overall view of carbon dioxide emissions reductions, I basically believe, especially in the developed world, that we should more or less make it illegal to make devices, power plants, automobiles that release carbon dioxide to the atmosphere. That we've reached the stage of economic development where we have to just consider that it's no longer appropriate to use the atmosphere as a waste dump for our industrial wastes. And so my interest in this subject comes out of the fact that we as a society don't appear to be dealing with this problem appropriately. Since I have 2 minutes, I don't want to say all the possible negative outcomes, but but just to say that there are a huge bunch of other risks. I think actually some people have suggested that these options might be used in sort of a risk reduction mode, but I think that the issue of international political risk is a real one. The risk of complacency, that people might feel, oh, well, this is working, we don't have to work on emissions reduction. Chemical risk, I do a lot of work on ocean acidification. These options don't deal with anything with ocean acidification. Ecological risk, after Mount Pinatubo, 20% of the radiation came down in diffuse radiation that spurred the growth of understory and forests. We have no idea what this sort of increase in diffuse radiation will do to natural ecosystems. Management risk, that these kind of options could obviously be poorly managed, and there's all kinds of other risks that other people can think of. And so, I think we're in a situation where there are great risks. There are also great potential to reduce risk. Again, I would like to remind you about the potential threats to tropical agriculture from overheating, and that right now we have little knowledge, and that we need to develop that knowledge in order to have sound responses to this problem. So I'll stop right there.